So today I was actually able to get access to the Tucker Wildlife Sanctuary. And so everybody should probably have downloaded a sheet of paper, multiple sheets, multiple pages. This is the field trip guide. We're going to go through all the questions and you can fill them out, take pictures of them, and then email them to me as a JPEG or whatever type of attachment you can do. So question number 1, what is the geographical setting at Golden West College? Well, obviously we're not Golden West College, but if you realize what the college looks like, it's flatland. We have now traveled out of the flatlands up into the mountains. So these are the San Ynez Mountains, kind of the foothills of the San Ynez Mountains. So the Tucker Wildlife Sanctuary is run by Kelsey Fullerton. Most of the work here is voluntary. And so question number 2, what is the general changes in elevation as we move from our college to this destination? Well, we actually increase in elevation. We're going to see active streams, completely different ecosystem than what you would see at the college. So that's question number 2. Number 3, what is the general topographic / geological setting of our surroundings today? Well, we're in a canyon. And as we go up the trail, you'll see evidence that we're in a canyon. And this canyon has been down cut by the river that we're going to visit next. And that basically is the geographic setting. Geological setting. Active stream erosion. So this is a photograph of the shot of the entrance to the sanctuary. Because of the coronavirus, the entire area around here is roped off. They're not allowing parking. They don't want to encourage people to come up to these areas. We got a lucky shot where we get to come up here and video record. And so let's go on in. And one of the first questions is, question number 4, how was this area formed? Active stream erosion. So active stream erosion. Now across here, there are a couple of oak trees. And we have an oak tree like this on campus. And the age of the oak tree on campus, it was planted in 1975. This oak tree, though, however, is about 200 years old. Its source of water is natural. The one on campus we artificially water, so it grew a little faster. So the age of the oak tree here is about 200 years, so it's seen an awful lot of history. That's why this area is very fragile. So if a fire were to occur, it would take out vegetation that had been in place for a long time. And unfortunately, non-indigenous vegetation, we're going to see some of that, disrupts the whole ecosystem and makes the region prone to fires. Number 5. So A, what is the age of the oak tree? 200 years old. 5A, the one at Golden West College, was planted in 1975. The next question is, who is Henry? And is he out? So B is who is Henry, and C is he out? Well, Henry lives here. There's some fresh lettuce. But I don't see Henry. Henry is a tortoise who should be out this time of year. They like this type of weather. It's fairly warm. So maybe Henry's underneath this little shade right here. Oh, there's Henry. Way back there. I don't know if you can barely see Henry. He's a desert tortoise. He's a threatened desert tortoise because their critical habitat is being destroyed, fragmented by development. Big solar projects in the deserts are really impacting the desert tortoise because they're developing these solar farms on critical habitat areas. Elevations and basins about 2,300 feet in elevation, prime desert tortoise habitat. So as we walk through the sanctuary here, what's neat about this is that if we were to go back in time 10,000 years in Orange County, so Tustin, Orange, Costa Mesa, all the major cities there looked a lot like this area looks today, minus the park bench. There would have been little ponds of water like this with turtles, and I know there's turtles in here, so the turtles live in water. Tortoises live on land, so the easy way to remember that is sea tortoises and sea turtles and land tortoises. And I don't see any turtles here today. There are generally quite a few out sunning themselves on that rock. So we're going to walk through the sanctuary here. We're going to go down to the stream and look at some of the rocks. The vegetation here, there's live oak, there's scrub oak, there's succulent plants like these. So this is kind of what we call a transitional zone, where you're moving from a more arid environment in the basins where Orange County is, City of Orange, Tustin. And as you move up into the mountains, the higher elevations are cooler and they tend to have a lot more precipitation. So here's a cacti that is down. I don't know if it is being pruned because it was in the way or just fell down. So now moving into the stream, which is actually active because of all the rainfall that we've had. So we're coming up on question number 6. The river wash is what type of a geological setting? So what type of a geological setting is a river wash? Well, they're erosional. Water is the most erosive force in nature, and consequently it's also responsible for the deposition of rocks. So a lot of sedimentary rocks are formed in water-rich environments, and yet at the same time water can be the most erosive force in nature. So we're coming down to this river basin here. This river basin is what actually has cut through these mountains. So imagine that these mountains, from one side of the basin to the other, that these mountains are once connected. They have been dissected, cut down by the river system. Now, if you look at the river that we currently see in operation, flowing along, this no way is representative of past river systems. So at the end of the glaciations, the last glaciation, the Wisconsin glaciation, as those glaciers melted, Orange County, Southern California, was cooler and wetter than it is today. So these streams would have been highly more active. And you can judge here by just looking at the amount of material. You'll see very fine-grained sand material intermixed with some cobble size and then boulder size. And here's a very large boulder. Just to give you an idea how large this boulder is. There's your outline for the field trip. And so the answer to number 6, the river wash, what type of a geological setting is this? This is erosional, and it's still actively eroding. So a lot of these rocks are not in situ. In other words, they've been transported by this river. And look at the size of this boulder here. That tells you that this river system has had periods of flooding. Now as I look across the little creek right here, on the side of the cliff here, kind of interesting. That is a good example of an unconformity. Notice that the overlying red unit has rounded cobbles in it. And then below that, this lighter color material is more of a sandy, finer grain material, and its bedding plane is different. And then you move down and you get more into another rounded, larger size cobbles. So this definitely is a good indicator of different environments of deposition. Larger material that was brought on by faster, swifter moving water. The finer grain material would have been deposited by slower moving water. A lot of these different settings can be set on climate changes and others on tectonic events. So when mountain ranges start to uplift, the gradient is increased. Gradient means water can move at a faster rate. Faster moving water carries more material with it. Okay, I'm going on to the second page now. What rock types are found in the river channel here? Well, there's definitely granite. There are shales. This rock here, very dark. A mafic rock, and right next to it, very small little piece of andesite. So there's an andesite, and then there's a conglomerate. Well-rounded fragments. These rocks here are shale. So the larger rock here, mafic, igneous. This would be a porphyritic andesite. This rock here, very light, very felsic, lots of microminerals in it, some quartz, biotite, plagioclase. This is a typical granite, very felsic granite. So the rocks that are in this setting vary from sedimentary rock shales to volcanic rocks to sedimentary rocks. So there's a whole sequence of rocks in here, and most of these rocks are out of place. They have been brought down from the upper mountain range by this river system and deposited here. So the finer grain material, the sand, this is an important thing to note. The beaches along coastal California, Huntington Beach, Newport Beach, all the way down to San Diego, up and down the coast of California, our beaches, the sand that you see at the beaches today originate from the weathering and then erosion of granitic rocks in mountains like this. That fine-grained sand is then going to be carried down the streams by river systems. Those river systems then would flow into the Pacific Ocean. That sand would then be distributed up and down the coast by the longshore current, and then deposited onto the beaches by the waves. We're losing our beaches because we have dammed all the rivers. The damming was done to build water reservoirs, but at the same time, when you trap the water, you also trap the fine-grained sand. And that's why today we're in trouble. Our beaches are eroding because they're not receiving enough sediment because we have dammed the rivers. And we're going to look at one of those. Number B, second page, number B. Are there any geological hazards in this area? Well, there are homes that are kind of built right next to this stream here. You can see a big concrete barrier, so flooding is certainly an impact. The canyon itself, this is called the chaparral, and the chaparral is a biological community that builds up a lot of underbrush, and the way it gets rid of that underbrush is it burns. So this is a biological community that is designed to burn, and that's not a big deal. It burns, it regenerates itself. The problem is that we build homes in the chaparral And when the chaparral goes through its natural biological cycle, when it rejuvenates itself through fire, homes that are built are consumed. So there's a lot of homes in this area built right within the chaparral. So this area is prone to flooding. It's prone to the possibility of fire. And then after fires, landslides. Because of the steep walls here, this area is very subject to landslides. So number C says, in addition to weathering, what are the geological processes that are occurring here in the wash? Well, the geological process basically is two things: erosion, transportation, and deposition. This is what streams do. They erode, they transport that material, and then they redeposit it in another place. Number 7, name the biological community of Sand and Mountains. This is the chaparral, the Spanish word for ranch. This is the chaparral. And what's unique about this biological community, number A, is it is prone to burning. That's how it regenerates itself. So how does this biological community stop erosion of the hillsides? Well, the root structure stabilizes the soil. The trees themselves actually stop the impact of raindrops on soil. So trees are a really good way to stabilize soil. When a fire goes through a region like this, that canopy, those leaves are destroyed. And then when it rains, the raindrops can impact directly onto the soil, resulting in soil erosion. Okay, our next question, number 8. We're going to have to hike up the hill, so we will answer that question next, number 8. So second page, question number 8, asks about soil horizons. We've studied soil horizons when we talked about weathering. And soil horizons in mountain areas like this are very limited because the steep topography here erodes those profiles. So here there is a little bit of organic material, a little darker material at the top. That's the organic horizon, the O horizon. Below that, a little bit more clay material. And as you move down, the soil contains more rocky material. So there's kind of 3 horizons here. There's a rocky, which is the mineral zone. There's the intermediate zone in between, the clay zone, which has some rock within it, and then organic material. So this is a very poorly developed soil. It's poorly developed because of the topographic setting. It's in a canyon area, steep topography, subject to runoff. So question number 8, just to rehash it, just to make sure everybody gets the answer. 8 says, what type of soil profile exists on the hills? A very poor one at that. One that you can possibly classify into 3 distinct zones. A very, very thin organic zone. Underlying that, a layer of clay. And then below that, the oldest profile is going to be the mineral zone, the weathered rocks. So this is a good spot also, not so much for soil, but we can notice that there's a red coloring in these rocks here. So this starts to entertain another question, as I have to flip my page. So number 9, what are the elements or compound that results in the red color of the soil and the surrounding hills? So it's pretty obvious that this is a nice red color. This is due to iron oxidation. And when we see rocks that have this red color, this red colorization is due to hematite, which is Fe2O3 iron oxidation. Now notice that the particles that make up the side of this hill here are pretty rounded. So these are classed of granites and shells and different type of rock This is really good evidence of pretty good weathering and transportation since everything's rounded. So if we were to compact this material, if we would send it through compaction, through diagenesis and lissification, what type of rock would this form? Well, since the fragments are rounded, it would be a conglomerate. If the fragments were angular, we would call that a breccia. So number A, are all the rocks well weathered? We'd say yes. What is the general shape of the rocks? B, rounded. C, if the material on the hillsides were to form a rock, the rock would be a conglomerate. So interesting thing about this is that we have red soils, lots of iron oxidation, and as we look at the upper part of the hills, they lose that iron oxidation and they're more of a greenish tan color. And that greenish tan colorization is due to lack of iron, and we'll talk about that next. So moving on to question number 10, we'll kind of pan around here and give you a good perspective of what the setting looks like. We're going to move from red colored rocks to rocks that are not red, that are more green. So you can see some erosion. Look at the big boulder down there. As it rolls down this canyon, eventually that material is going to slam into those houses down there. So the reason that some of these sediments are red in color and others are greenish in color is due to iron oxidation and iron reduction. So the red is iron oxidation. So this is iron with the presence of oxygen. The overlying sediments that are much younger don't have the oxidation of iron. And there are two things that can result in the non-oxidation of iron. So this would be iron reduction. Iron in the presence with no free oxygen. That can occur because of biological activity that deprives the dissolved oxygen in water, or that the material was deposited in a deeper water environment. What gives it away from one of those two hypotheses is a rock that we find throughout the trail here. I'm going to focus on one of those rocks. This is a piece of chert. So chert is a general word to describe what we call sedimentary quartz. So there's three varieties of it. There's the black, which is flint, the gray we call chert, and the red is referred to as jasper. So since there's so much chert here, and some jasper, and a fair amount of flint, this would suggest that these rocks were formed in a deep water environment. So something occurred here where the water level went from shallow, so shallow water environments generally contain more oxygen. Deep water environments contain less oxygen, and especially with the presence of sedimentary quartz, cherts, jaspers, flints. So question number 10, what are the geological and environmental conditions that resulted in the formations of these sediments within the hills? These were definitely formed in an offshore environment. So all these hills that we see around us were formed in an environment that was oceanic. So what was occurring is that sediments were eroding off the continent and being deposited offshore under the ocean. And so that's the environmental conditions. So that's question number 10. Number A, what are the sedimentary rocks, or where were the sedimentary rocks formed? A lot of them were formed in what we called submarine canyons. These would be offshore canyons. This material was then being eroded off the continents and shed into these deep submarine canyons. And that's why we think it was a submarine canyon environment, because of the presence of the siliceous quartz, the cherts. So number 11, what was the geological force now that takes these sediments from the ocean and puts them onto the continent and into the foothills of the Sand Mountains? And that force is what we call accretionary tectonics. So what accretionary tectonics implies is that microcontinents that originated in Australia and Antarctica were brought across by a plate, and these microcontinents from a small continent called Rhodia stuck themselves onto the North American continent, and this process is called accretionary tectonics. This is where sediments are accreted onto the continent. So accretionary tectonics. So the process for number 11 is accretionary tectonics. Number 12, why are some of the sediments red in color and others green in color? There's two hypotheses. One is that the red sediments were formed in shallower water, rich in oxygen, and iron was oxidized. The green color sediments is iron that did not have the presence of oxygen. So this is what we call iron reduction. Two things could have caused that. One was that the sediments were somehow formed in deeper water, that the water level increased, the depth, sea level rose, tectonic event occurred where these mountains were downdropped, the submarine canyon was all downdropped, exposed to deeper water, or biological activity. There was so much biological activity that the biological activity robbed the water. Most geologists would probably speculate that some type of a tectonic event occurred, exposing these sediments to deeper water conditions. And that's why you see the lack of red coloring, more of a kind of a greenish tan color. And it's a steep contrast as we move down. You can definitely see the red colorization is more prominent. Definitely oxidation and the red, reduction, iron reduction. That is iron that is not formed, not oxidized. So that is the answer to primarily question number 12. So now what happens to the sediments as we move from the mountains to the basins and to the valleys where cities like Orange, Tustin, Huntington Beach, Costa Mesa? We're going to explore that at our next little stop. So at this location, I'm on a ridge between two basins. So this is the basin we just hiked out of. And then on the other side of this ridge, another basin. So rivers are acting like a hot knife to butter, and they're literally cutting down through these sediments, and they're taking these sediments and they're redepositing them into the basins where the cities such as Orange and Tustin and Santa Ana now occupy those valleys. So as we move down from the mountains to the basins, the size of the sediments are going to become smaller. Eventually, when the Santa Ana River travels across cities like Fountain Valley and Tustin, prior to human channelization of the Santa Ana River, it used to be a meandering stream, and it would carry soft sand with it. That sand was then discharged in the Pacific Ocean, distributed up and down the coast by the longshore currents, and then summer wave action from the south swell would place that sand onto the beaches. That process is being interrupted today, and we're going to take a look at one of those areas where that is being largely interrupted. So our next stop will be right down at the bottom of this basin here. Some good evidence that these rocks were formed in a deep water environment is right here. These are some of the chert, the variety flint. Very dark colored rock. This is hard. This will scratch glass. This is a sedimentary version of quartz. I find this rock scattered throughout this trail here as I'm hiking up into the mountains. The clast, the material that makes up these hills is full of the sedimentary version of quartz. And that is probably really good evidence that these rocks were formed in a deep water environment. So I'm at the bottom of this canyon. Very active river system. This one has a fair amount of vegetation in it because of the amount of water here. So as this river flows along, carrying with it sediments, it has a very dramatic ending, a dam. So what's behind this dam is sediments. And this is one of the primary reasons why beaches in Southern California and in coastal California in general are eroding. Because as we move from the mountains have high elevation, therefore the rivers are going to flow at a very fast rate because of the gradient. So one of the questions is that what happens to the sediment as we move from the mountains into the basins? Well, it becomes smaller. So boulders become cobbles, cobbles become granite, granite, pea gravel, and then pea gravel eventually to sand. You can see some of that sand here on the banks. So all this material is being blocked, the fine-grained sand is being blocked from hitting the ocean, from being deposited or discharged into the ocean because of this dam. And this is just one of many dams. The purpose of the dam was to provide a reservoir for cattle. But dams do two things. They dam up water, but they also dam up the sediment. And eventually they silt in, and as this one has. The Prattle Dam right off the 91 freeway, they had to actually make that dam higher and wider because it was filling up with sediment. So this is one of the many tributary streams. So question number 14, the smaller washes drain into basically the Santiago Canyon wash. So that's the Santiago Canyon wash, that's the answer number 14. This system then discharges in the Santa Ana River. The Santa Ana River originates with its headwater in the San Bernardino Mountains. It discharges into the Pacific Ocean. So question number 16, where does the Santa Ana River discharge in the Santa Ana into the Pacific Ocean? Right at what's called the jetties. This is the boundary between Newport Beach and Huntington Beach. So that's where that number 16, that's where the Santa Ana River discharges into the Pacific Ocean. Number 17, where did the soft sands of Huntington Beach originate from? Well, right here, mountain ranges like this, like the Santa Ana Mountains, Santa Monica Mountains, San Gabriel, San Bernardino Mountains. And throughout these mountains, there's these little river systems that for millions of years have been carrying sediment. And now since humans have come along, we've kind of stopped that process with dams. So what type of rock, number 18, what type of rock weathers the sand that we find on our beaches in Southern California? Granites. Because the main composition of our beach sand is quartz. And these quartz particles have weathered out of felsic granitic rocks that are very rich in quartz. Quartz is very resilient. It has a very strong bond. It's a covalent bond. And quartz does not break down. SiO2 does not weather out. It does not break down. It simply just weathers into smaller pieces. So we have 2 more stops, and then we'll wrap up this field trip. Okay, question number 19. Ask what type of organism would want to pollinate a white flower. So this little stalk here grows a white flower, and you'll see these throughout this area. This one here is almost ready to bloom. Come back in about another week and it'll be blooming. As I pan around, you'll see some of these. So generally flowers tend to be very bright colors. Yellows, pinks, purples. So what type of organism is going to pollinate a white flower? Well, something that's nocturnal. And bats is the answer. In October, the Tucka Wildlife Preserve has a bat festival. Bats seem to migrate. There's little caves in these cliffs. And bats in October seem to migrate at night. They go from cave to cave. And so there's a huge bat festival. So the answer number 20, bats are what pollinate light-colored flowers, white flowers. We have one more last stop, and that'll be at the beach where the Santa Ana River discharges into the Pacific Ocean. And I'll go over a little bit of the material that is being deposited there and kind of give an overview of the last questions on the page. So this is the Pacific Coast Highway looking north towards Huntington Beach. The Santa Ana River crosses the Pacific Coast Highway at this point. To the south is the city of Newport Beach. So the Santa Ana River acts as a political divide between the municipalities of Newport Beach to the south and Huntington Beach to the north. So this is the Santa Ana River, and it discharges here into the Pacific Ocean. And the sand that you see in the background, the sand covering the beaches, basically originated up in the Santa Ana Mountains and surrounding mountain ranges like the San Bernardino Mountains, the San Gabriel Mountains. It's all due to the decomposition, the breakdown of granitic rock. Quartz is very resistant to weathering, and so this quartz sediment is transported. And just to kind of recap, as we move from the mountains towards the coastal setting here, the particle size decreases. It becomes finer and finer. And that's primarily because the river in the lowlands down here flows at a slower velocity. It is not able to transport as much sand or large size material, so that all it can transport at this point is fine grained material and sand. This process is being stopped due to the construction of dams. So this is the last of our field trip sequence for the spring semester of 2020. Certainly one that will be remembered. A strange semester.